Two tree ensembles dominate tabular ML. If you pick the wrong one, you waste days. Here's the rulebook. This is the workflow you'll know how to run when we're done, which compares two ensemble models with your metric, and then selects the best under your constraints. I'm Professor Pi, teaching AI foundations with simple Python. Ensembles like random forest and gradient boosting are the go-to tools when you have tabular data and you need reliable predictions fast. They solve classification and regression problems where features mix numeric and categorical signals. Success looks like higher decision quality on held-out data and a model that fits your latency and interpretability needs. Practitioners reach for scikit-learn versions because they are stable, familiar, and good for prototyping before scaling. At a high level, random forest builds many independent trees and averages them. That reduces variance and makes training parallel. Gradient boosting builds trees one after another, each one focused on fixing the prior mistakes. That tends to improve raw accuracy, but requires careful tuning to avoid overfitting. We will build a small classification comparison. You will see a baseline, then a random forest, then a gradient boosting run, then a tuned boosting model, and finally a decision rule that picks the best model by metric. The goal is to leave you able to compare these models on your own data without guessing which one to trust. Now we'll create toy data and a baseline. This snippet generates labeled toy data and establishes a no-skill baseline using scikit-learn. The function makeClassification creates features X and labels Y with a fixed seed for repeatability. The call to train test split partitions the data so we can evaluate on a held-out set. A dummy classifier with the most frequent strategy learns the majority class, giving us a simple floor to beat. Finally, accuracy score measures how often predictions match Y on XT, and the result is rounded for readability. If your classes are imbalanced, this baseline can look deceptively strong. Knowing it prevents overestimating real progress. The printed baseline ACC shows the naive benchmark your models must surpass. Next, we will train a random forest and score its ranking ability. This example trains a random forest classifier in scikit-learn and evaluates its ranking quality with ROC AUC. The variable RF is configured with n estimators and max depth to control the size and complexity of each tree. After fitting on XTR and YTR, the method predictproba returns class probabilities, and we slice the positive class column into RFP. The function ROC AUC score compares those probabilities against YTE to measure how well the forest separates classes, regardless of threshold. Increasing n estimators generally improves stability at the cost of time. Increasing max depth can capture more interactions, but risks overfitting. The printed RF AUC reflects the forest's discrimination power on unseen data. Now we will train a gradient boosting model and compare. This code fits a gradient boosting classifier in scikit-learn and directly compares it to the random forest. The object GB builds shallow trees sequentially, each correcting errors from the previous, with learning rate and n estimators controlling the step size and number of boosting rounds. After training, predictproba yields probabilities for the positive class, and ROC AUC score produces GB AUC score on the test split. A simple conditional sets winner based on which AUC is higher, surfacing the better default choice for this data. Lower learning rate often needs more n estimators to maintain accuracy, but can generalize better. The printed winner tells you which default ensemble currently performs best. Next, we will tune the gradient boosting model with cross-validation. This snippet tunes gradient boosting classifier with scikit-learn's grid search CV to improve AUC. The object GS explores combinations of learning rate and N estimators using threefold cross-validation, and scoring equals ROC AUC. After fitting on XTR and YTR, best estimator underscore retrieves the tuned model GB best, which is then evaluated on XTE via predict proba and ROC AUC score. Reducing learning rate usually needs more N estimators to keep accuracy stable. The trade-off is slower training, but potentially better generalization. Expanding the grid widens the search, but increases compute time. The printed GB-tuned AUC shows how much boosting can gain when you set the right knobs. Finally, we will pick the model and inspect probability quality. This example finalizes model choice by comparing random forest and tuned gradient boosting, then reports probability quality with scikit-learn's log loss. The variable best selects GB best if its AUC beats RF AUC. Otherwise, it keeps the forest. The call predict proba on best produces calibrated looking probabilities, which feed into log loss to penalize confident mistakes more than mild ones. Lower log loss means sharper, better calibrated predictions, complementing AUC's ranking view. If you later tighten learning rate or add trees, revisit both AUC and log loss to balance discrimination and calibration. The printed final log loss communicates how trustworthy your chosen model's probabilities are. In a real project, this pattern maps directly to a simple pipeline. Train with a reliable baseline. Measure ranking with ROC AUC. Tune boosting with cross-validation. Then validate probability quality with log loss before you deploy. Recap. Random forest is parallel, robust, and simple to tune. Gradient boosting is sequential, often more accurate, but sensitive to learning rate and tree count. One caveat. Defaults rarely win on every dataset, so measure both discrimination and calibration. Next step, tune the learning rate and number of estimators for gradient boosting on a wider grid, and track both AUC and log loss over the validation folds. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.